So today's lecture is about circular motion. There's a lot of circular motion. It may seem like yeah, things that go in circles. How complicated could that be? That's actually really complicated. There's a lot of math we could do to go in circular motion. You do circular motion in this class. We do circular motion in physics 55. You can do circular motion. The quantum mechanics version gets even more complicated. Yeah, it just keep building up on it. Rotating things is surprisingly complicated. But the goals for today are we want to be able to convert between degrees, radians, and revolutions, understand centripetal acceleration, and understand why centripetal acceleration goes as a v squared. If we have some extra time, we'll do a little bit of estimation at the end, because you have some estimation on your homework. Okay, so first we'll talk about angle. So you remember, like back on the first day of this class, we did position and velocity. So everything angular is kind of like the stuff we're doing here. And instead of position, we have angle. Instead of velocity, we have angular velocity. Instead of acceleration, we have angular acceleration. It just keeps going along like that. Yes?
Did you upload the notes?
Oh, did I forget to upload the notes? I totally could have. Of course, this is it. Just a minute. Assignment, files. Files. Lectures. Yes, I did. Physics 20 lectures. Oops, wrong here. Okay. Up to internet tubes, they should be uploaded. Okay. So basically, we're going to start with angle and we'll go from there. Okay, so we want to have a really good understanding of angle. The most natural units to measure angle in is this thing called radians. These are, a radian isn't really an angle, or isn't really a unit. We kind of think of it as a unit, kind of like centimeters or whatever, but radians are really a fake unit. You can kind of like get rid of them. They're, you know how today we were talking about fractional error. Of those of you who are in lab, at least, we were talking about fractional error. Fractional error doesn't really have units. It's a ratio of say a distance and a distance, or a mass and a mass. Angle is the same thing, right? If you have a triangle, like it's the sine, it's the tangent angle is this over this. So it really just comes from a ratio. So it really doesn't have units. We give it this fake thing called radians, because they're kind of helpful to think about, but radians aren't real units. And you can just kind of get rid of them. There's also degrees. You're probably more familiar with degrees. They're older units. More people use degrees for other things outside of physics. There's also something called a revolution. Revolution is, so one revolution is all the way around. So this comes up a bunch when you're like using, you're looking at a car. So your car has RPM, revolutions per minute. So you're saying how quickly is the engine turning? You did it in full revolutions. You could do it in degrees per minute. You'd have to, basically it'd be 360 times bigger. Or you could do it in radians per minute. You'd have different versions. So the unit conversion is 2 pi radians is 360 degrees is 1 revolution. I'm going to show you why that is. Okay, so I'm going to show you what the definition of a radian is. Okay, so here we have a circle. And suppose we take a little piece of string and we get a piece of string, we cut it so it's just long enough to go from the center to the edge of the circle. So it's 1 radius long. Okay. Then we take that piece of string and we wrap it around the outside of our circle. And it'll make it to about there, right? And that's how all the longer the string will be, right? Because we cut it so it's the radius of the circle long. You take that angle, that is 1 radian. The definition of a radian is you take the distance around a circle of 1 radius, the angle subtended will be a radian. Okay, how many radiuses go into a full circle? Well, how many diameters go into a full circle? Like if we take a rope that's the length of a diameter, we take another rope that's the length of the diameter, we start wrapping it around, how many times will that rope go around? Or how many of those ropes will we need to go around? No, well, the first one will make it to about here. Next one over here, next one down here, and then we'll need a little bit more. It's pi. The definition of pi is pi is the circumference divided by the radius. So if there are pi diameters in a circle, how many radiuses are in a circle? 2 pi. Yeah, so there are 2 pi radiuses to go around a circle. So there are 2 pi radians to go around a circle. Hence the conversion between radians and revolutions is there are 2 pi radians in 1 revolution. How many degrees to go around a circle? 360, right? That's the definition of degrees. You need 360 degrees to go around a circle. So 360 degrees is 2 pi radians is 1 revolution. Questions? Everyone get the concept here with what I mean by radian is a radius going around? Okay. So that's angle. Oops. You weren't supposed to see that. This is not calculus-based physics. Okay. Omega is angular velocity. Do you remember what, so remember backing up, we had position, and then we had velocity was change in position over change in time. And then acceleration was change in velocity over change in time. Remember that this is like the first couple days of this course. So position, velocity is a change in position for change in time, and then acceleration is change in velocity for change in time. We're going to do a similar thing, except for instead of starting with position, we're going to start with angle. So angle is just angle, theta. Then angular velocity is this thing. This looks like a W. It's not a W. It's an omega. So side comment about Greek. This is the capital omega. That's the little omega. New Greek letter for the day. So little omega is the variable people use for angular velocity, typically given in radians per second. So omega is the change in angle over the change in time. Just like velocity is position per time, angular velocity is angle per time. So let's check the units of omega. So what are the units of angle? Shout it out. Degrees. Well, okay, but we're going to be physicists, so we're going to use radians. Radians. Time. Units of time. Seconds. So omega is in radians per second. Except for that, radians are fake units. So if you want to, you can just call it 1 over seconds. So we have to distinguish three things. There's frequency, omega, and period. All of these three things are used to describe how fast something is turning or how often something happens. So period, that's how long it takes it to go around one revolution. Omega, that's how long it takes it to go through one radian. Frequency, omega is how many radians it goes through every second. Frequency is how many revolutions it goes through in every second. They are related to each other by frequency is 1 over the period. So if you have something that's turning slowly, like the Earth turns once a day. So the period of the Earth is 1 day. So and it's convenient because that's a long time to use period. If you have something turning quickly, like your engine, so when your engine's, the shaft in your engine is turning quickly, you don't say, well, how fast is my engine spinning? Well, it goes around once every microsecond. Or millisecond is more like it. It goes around once every millisecond. You don't say that because that's a small number. Instead, people like big numbers. So instead of reporting the time it takes to go around, they report how many times it goes around every second, or actually they do it every minute. So instead of reporting the period, they report the frequency. So you could say the frequency of the Earth is once per day. And you could say, so frequency is 1 over period. 1 divided by time. Omega is 2 pi over frequency. And why is that? Well, no, sorry, 2 pi, back up. Sorry, 2 pi times frequency. 2 pi over period. Okay, 2 pi times frequency. So if the frequency is how oft is how many times you go around every second, you could also ask how many radians do you go every second. So imagine you're running around this circle. If you say how many times you go around every second, well, you go through a lot more radians. Every time you go around, you go through 2 pi radians. So the number of radians per second is 2 pi bigger than the number of revolutions per second. So omega is 2 pi frequency. Because by convention, omega is in radians per second and frequency is in revolutions per second. So to convert between the two, you need to multiply by 2 pi. Okay, if you combine these two equations, you get the omega is 2 pi over period. Okay, so I know these are the equations, you just have to write them down somewhere. Hard to remember sometimes. The little equations are always the ones that get me. So it's good to write these down. Frequency is 1 over period. Omega is 2 pi times frequency. And omega is 2 pi over period. There's also a thing called angular acceleration, which is change in omega for change in time. So remember how we had position, velocity, acceleration, x, the change in x over change in t, and then change in v over change in t? Well, now instead of to get angular acceleration, we take the change in angular velocity over time. So it's just like regular velocity acceleration, except for replace position with angle and angular and velocity with angular velocity. So it's just sort of the same pattern. But we'll talk about angular acceleration more at a later date. I'm just kind of giving you a preview for that one. Okay. You might want to add these to your variable table. So we have a bunch of new variables I've just introduced. I've introduced angle. I've introduced omega, t, f, and alpha as well. These are all variables you could put on your variable table if you're keeping track of that thing. Okay, so let's do some conversions to make sure we're all on the same page. What is 60 degrees in radians. Make sure you have a clicker. And 5, 4, 3, 2, 1. Okay, so 60 degrees, 60 degrees times there's 360 degrees in 2 pi radians gives, well, 360 is 6 times 60. So that'd be 2 pi radians over 6, which comes out to 1/3 pi radians. But radians are fake units, so we can just say it's 1/3 pi. Okay, we're going to use this example for a bunch of time, so take some time to think about it. A person walks at speed 1 meter per second around a circle of radius 10 meters for 2 seconds. Through what angle have they walked? So here's our circle. They're going at a speed of 1 meter per second. And they go for 10 seconds, or they go for 2 seconds. The radius is 10 meters. What angle will they have walked through? Sorry, let me, all right. You already clicked it in, click it in again. I just started the thing. Okay. If they are walking at a speed of 1 meter per second for 2 seconds, how far have they walked? 2 meters. Okay, how far would they have to walk to go 1 radian? 10 meters, right? Because the radius is 10 meters long. So in order for them to go around by 1 radian, they'd have to go 10 meters. So what angle have they gone through? You can change your answer if you need to. Okay, how about 10 more seconds? Five, 4, 3, 2, 1. Display. Okay, so there's some discernment. All right. So we have a circle. The circle has a radius of 10 meters. If we take a string that's 10 meters long and we wrap it around, that will go 1 radian. So this distance here is 10 meters, correct? How far did we go? 2 meters. So how much of a radian did we go? 1/5. Because we went 2 of 10. Questions? Okay. A person walks at speed 1 meter per second around a circle of radius 10 meters for 2 seconds. Same situation. What is their angular velocity? What's the formula? What's the definition of angular velocity? Sorry, changing angle. Okay, 15 more seconds. Five, 4, 3, 2, 1. Display. Okay. So what's our change in angle? 0.2 radians. Radians are fake units, so 0.2. And our change in time? So we have 0.1 radians per second, or 0.1 per second, if you prefer. Okay. Notice something here. Up here, our angle was equal to the distance traveled, or was equal to, sorry, let me put it this way, was equal to our velocity times time, which gave us our distance traveled over the radius. This quantity here, if we refer to this as x, then theta is equal to x over r. Okay, if we divide both sides by delta t, theta divided by delta t, so we get d theta, we can call this our change in theta, is going to equal our change in x over delta t r. So I literally took this equation here and divided both sides by delta t, right? What, and d theta dt we have a name for. That's omega, right? But dx dt we have a name for. That's v. So the equation you get is omega is equal to v over r. So we could have used this equation here as well. So this is an equation that a lot of people remember. V is equal to omega, or omega is equal to v over r. So omega is equal to our velocity, 1 meter per second, over our radius, which is 10 meters, which gives us 0.1 radians per second. All right. Questions? There's a couple different ways of solving that one. Let's do another one. A person walks at a speed of 1 meter per second around a circle of radius 10 meters. What is the period of their motion? AKA, how long does it take them to get around? Somebody help us out. What's our relationship between period and omega? It's 2 pi. Okay, 10 more seconds. 5, 4, 3, 2, 1. Stop. Display. So we could say we're solving for t. T is 2 pi over omega. That's 2 pi. We've already decided that the omega is 0.1 radians per second. So apparently the period is 10 divided by 0.1, which is 20 pi seconds per radian, but that's a fake unit, so it's just goes away. So it's 20 pi seconds. So that's one way of thinking. Another way of thinking about this, we're walking at a radius, we're walking at a speed of 1 meter per second around a circle of radius 10 meters. How far is it around the circle? Yeah, the distance around the circle is 2 pi r. So we have 2 pi r is our distance. Our velocity is 1 meter per second. Velocity is distance over time. We're trying to find time. So time is distance over velocity. So distance is 2 pi r, but r is 10 meters. So I'll just put that number in, 2 pi r over our velocity, which is 1 meter per second. And we get 20 pi seconds. Okay. I think there was a bunch of concepts there, so I'm going to re-summarize them. Okay. So we have number one, we have the conversions between our different angle units. So we have 2 pi radians equals how many degrees? 360 degrees equals how many revolutions? 1 revolution. Okay. 2. We have the relationship between we have the definition of a radius. So the definition of a radius is that one radian, it goes around by 1 radius. So that's 1 radian. You take 1 radius and you wrap around, you get 1 radian. That tells you if you call this distance x and this distance r, then theta, if theta is measured in radians, doesn't work in degrees or revolutions, but if you're working in radians, and this is why radians are a really convenient unit in physics, if you're working in radians, then x is equal to, theta is equal to the distance around over the radius, just by the definition of what a radian is. Three, we can divide both of these by delta t. So we can take theta over delta t. So delta theta over delta t, delta x over delta t r. That is omega. Omega is equal to delta theta, delta t. That's true by definition. And velocity is delta x over delta t, which you knew already. That was just a definition of velocity. So we use those two definitions on that equation there, and we get omega is equal to v over r. I forget this equation all the time. I always forget, should I multiply or divide by r? So the trick is you check your units. Units of omega are radians per second, but that's just, radians are fake units, so I'm just going to call it seconds. 1 over seconds. Velocity is meters per second. Okay, so r is meters. So notice, if you take meters per second, you divide by meters, you get per seconds. So if you're ever curious, should I multiply or divide by r? Do whatever you need to do so that the units work out. Okay, so first equation, thing to remember. Second thing to remember. Third thing to remember. And I guess you should also remember these two definitions. Well, actually, I'll call that one thing to remember. That'll be number 4. And then this is really important to remember too, but you've already memorized that because that's velocity is distance over time. And you've been doing that for like 2 months now. Questions? Okay. Let's do centripetal acceleration. So, can somebody remind me the difference between speed and velocity?
Velocity includes direction.
Very good. Velocity includes direction. Okay. So when I say acceleration, A, as a vector, is defined as the change in velocity over change in time. There's one way to do that. And this is the way we've been doing it in the past, right? We were dropping things and they were accelerating, or you like had cars and they accelerate or whatever. The one way to change velocity is to change your speed. You change your speed, your velocity changes as well, because velocity is speed and a direction. So if you change your speed, you change your velocity. Another way to change your velocity is to change the direction. You keep your speed the same and change your direction. You are still changing your velocity. You're not changing your speed. You are changing your velocity because velocity is both the direction and the speed. Okay, so now we haven't done this yet. All of the accelerations we had so far in this class, the thing that has been changing is the speed, not the velocity, or not the direction. But now we're actually going to change the direction. Okay. Okay. And what we're going to do is we're going to have an object going around a circle. Okay, so we're going to have it, imagine this little dot, and it's going to like go around a circle. It's cruising around a circle. And this dot could be anything, right? We could be a car driving around a corner. It could be a satellite orbiting the Earth. It could be a piece of your crankshaft going around as your engine turns. Anything that's going around in a circle. Could be a piece of your wheel as you're driving down the road. So something that's turning. Okay, and it's accelerate and we're going to try to find what the acceleration of this point is as it goes around the circle. To make things simple, we're going to assume it travels at a constant speed. So if you think of this as a person running around a circle or a car driving around a circle or something like that, it's going to go at a constant speed. It's just going to keep going around. So it's not going to change its speed. It's only changing its direction. Notice, imagine at time t, it's traveling at velocity v. At some time t plus delta t, some time later, delta t later, it's traveling at a different velocity. The length of those arrows are the same because it's traveling at the same speed, but the direction is different. So that caused a change in velocity. So we can draw the change in velocity vector. Okay, so if my first velocity vector is like this, so that's the initial velocity, v0, and my final vector is like this, that's v final, or I could say one is just v at t and one is v at t plus delta t. Those are my two velocity vectors. This is the change in velocity. So notice, had they not turned, so instead of turning, if they'd just been the same, there'd be no change in velocity. Compare this to what we did earlier. So earlier in this course, we had a downward velocity at one time, and later we had a bigger down. So we would have a v naught like that and a v final like that. So if we wanted to find our change in velocity, we could go, our change in velocity would be like that, delta v. Okay. So that would be a change in speed causing a change in velocity. Here we have a change in direction is causing a change in velocity. Cool. Questions? Okay. Suppose the object is traveling at speed v. How far will it travel in time delta t? And I mean like the full arc distance, not the displacement. Like its full distance travel. Like if it had no odometer, how much would its odometer increase? Not sure, check units. 5, 4, 3, 2, 1. Stop. Distance. Distance. Okay, so it looks like B was fairly popular. Okay. Velocity is distance over time, delta x over delta t. So distance is velocity times time. So velocity times delta t. You can also check the units, right? Meters per second times seconds gives you meters. Okay, great. Yeah. So our velocity is our distance times our time. Or sorry, yeah. And our distance is our velocity times our time. So that's the distance around is that. Okay. What angle theta has the object gone through between time t and delta t? So to remind you, t is up here, delta t is sometime later. So between t and t plus delta t, there's some amount of time has passed. Through what angle? See this angle right here. What angle we have gone through between t and delta t? We're traveling at speed v. Radius is r. So you know how fast we're traveling. You know how long we're traveling. We're traveling a time delta t. You know how fast we're traveling. So you can figure out how far we traveled, v delta t. You know what the radius is. So using the definition of a radian, you should be able to calculate what angle we've gone through. Five, 4, 3, 2, 1. Play. Okay, people seem to like the first one. Okay, so what was our equation? We said theta is equal to x over r. So theta is equal to the distance, which is velocity times delta t over the radius, which is it comes from the definition of a radian. A radian is distance around divided by the radius, gives you the angle in radians. So the angle in radians is the velocity times the change in time over the radius. Okay, let's just make sure that makes sense. If you go faster, you'll go through more angle. If you travel for longer time, you'll go through more angle. If it's a bigger circle, you'll go through less angle because you'll have more distance to go to get around. So it sort of makes sense that the angle you go through is the velocity times the time divided by the radius. Okay, so now here's the kicker. We're going to put all this together. We're going to calculate the acceleration. So our acceleration, what, by the way, does anyone remember what the definition of acceleration is? Change in velocity over change in time. Okay, so our change in our velocity. Okay, so this one's going to take a bit. So this was our change in velocity. Okay, notice this is an angle here, theta. You see how this angle here is the same as that angle there? This is a right angle and that's a right angle. So if you turn, if this velocity is here and this velocity is here, this forms a little triangle like that. This angle is the same as that angle. Okay. Now, technically speaking, this isn't a right triangle, right? Because this sticks out just a little bit further than this one. But if angle is small, so we're going to make an approximation. We're going to say theta is small. If theta is small, then this little change in V is almost directly downward. Almost. So I'm just going to say, let's just pretend it's straight down. So I'm going to pretend that's a right angle. Okay. Then delta V is equal to V sine tangent theta. V naught tangent theta. Agreed? Tangent is opposite over adjacent. So opposite over adjacent. Okay. So in my acceleration, I've got V naught tangent theta. Okay. Over time, delta t. Okay. Pull out your calculators. Do you all know how to switch your calculators to radians? Switch your calculator to radians. Okay. We're going to take tangent of 0.001. What do people get? You don't know how to switch your calculator to radians, let me know. By the way, if you use Google and you use angles on Google, you just use Google's calculator, it assumes you're in radians. Unless you tell it. Did everyone get this? Is this kind of cool or what? Any guesses what the tangent of 0.02 would be? It's 0.002. Pretty wild, huh? Okay, there's a rule. It's called the small angle approximation. This is a small number, right? So if your angle in radians is small, then tangent of theta equals theta. Fun fact, sine of theta is also theta. Try sine of 0.001. What do you get?
As to why acceleration like the tangent, I'm a little lost on that.
Oh.
Opposite over adjacent. I got time.
Okay. So back up. We'll get to this using this small angle approximation in a minute. Let's go back to our calculation here. So share screen. Okay, so acceleration is change in velocity over change in time. Change in time just went over here. I have to change in velocity. Okay, so I'm going to go back up to my picture. I'm going to look for change in velocity. So this is my initial velocity here, is this red arrow, and this red arrow was my final velocity. And I'm going to use trigonometry to find the change in velocity. Okay, by trigonometry, if this is V naught, right? Well, that's V naught there. And this is delta V. Tangent of theta is opposite delta V over V naught. So delta V, multiply both sides by V naught, delta V is V naught tangent theta. So our change in velocity is V naught tangent theta, so I can plug that in down here. Okay. Cool. And okay. And I'm just going to refer to V naught as just V, if you don't mind, because there's only one velocity or one speed. Okay, so because of this rule, which you checked with your calculators, as long as it's a small angle, and this only works in radians. You try this in degrees, you will get the wrong answer. But if you do this in radians, we have a small angle in radians, the tangent is equal to the angle, as is the sine. Okay, so we're doing this in radians, and the angle is going to be small because we're going to go through a small amount of time. So the tangent of theta is just equal to theta. So V, we get V theta over delta t. But we already calculated what theta is. It's up there. We plug this in, this here into there. So we get V delta t over R over delta t. We get V squared for R. To summarize, acceleration is equal to V squared over R. This is a special type of acceleration. We'll give it a subscript C for centripetal acceleration. It's the acceleration you experience when you go around a circle. It's centripetal. Okay, so acceleration is a vector. This only gives us a magnitude, V squared over R. Which direction is it? It's down, right? Yes. Yeah. So the centripetal acceleration is always towards the center of the circle. So notice when we're at the top of the circle, the change in velocity is downward. So the acceleration was downward. Had we done this at the side of the circle, our initial velocity would be there, our final velocity would be there, and our change in velocity would be that way. If we were at the bottom, our initial velocity would be here, our final velocity would be there, our change in velocity would be this way. No matter where you are, you're accelerating towards the center, hence centripetal acceleration. So centripetal acceleration is the acceleration you experience towards the center of the circle as you go around the circle. And its magnitude happens to be V squared over R. That is like memorizable equation. Okay. Why don't we take, how much do I have left? Let's take a 5-minute break. I'll see y'all at 6:15. Welcome back. In the first half of lecture, we did two things. First, we talked about angles and circular motion. So we said 2 pi radians, 360 degrees, 1 revolution. And I realize now that that was really bad handwriting. That is an REV. REV, revolution. Rev is the abbreviation for revolution. Theta in radians at least, is distance around the circle divided by the radius. Omega is V over R, and omega, the definition of omega is d theta dt. Okay, we're gonna combine this omega is V over R with the other thing we learned, which is acceleration is V squared over R. So omega is equal to V over R, and centripetal acceleration is V squared over R. Write that in a little bit better handwriting. V over R. Okay, I'm going to solve for V here and plug it in there. So V is equal to omega R. So if I plug that into the acceleration equation, I get acceleration. Acceleration is equal to omega R squared over R, which simplifies to acceleration is equal to omega squared R. Okay. These are both true. These are different ways of calculating centripetal acceleration. One is V squared over R, one is omega squared times R. Notice something bizarre. If radius increases, does centripetal acceleration increase or decrease? If radius increases, does centripetal acceleration increase or decrease? Well, actually, it's a trick question, right? Because according to the top equation, if you increase R, R's in the denominator, centripetal acceleration will decrease. According to the second equation, if we increase R, R's in the numerator, centripetal acceleration will increase. Well, it depends what you hold constant. Yes, true. If we hold omega constant, so if we hold constant how quickly we're going around the circle, how fast the angle is changing, then increasing the radius will increase the centripetal acceleration. If we keep our speed constant, then increasing our radius will decrease our acceleration. So sometimes I ask this trick question on things where I say, if you increase the radius, what will happen to the centripetal acceleration? Okay, so that gives us centripetal acceleration. The other big topic for today is centripetal force. Equation for centripetal force, F equals ma. You need if something is going to go in a circle, it's got to accelerate, right? We agreed if something. Okay. Okay. So if we're going to go in a circle, we have to have we're going to accelerate, right? We got to accelerate towards the center. If you have an acceleration, you have an object that's accelerating, you need a mass. So F equals ma. We can take the acceleration and multiply by mass, and that gets us a centripetal acceleration. This is the force that is required to keep something moving around a circle. Let's do it this way. The acceleration. Okay, so y is the velocity squared. Okay, so we see. Let's focus on the equation. Force centripetal is equal to mv squared over r. Now you can use mv squared over r or m omega squared r. But we're gonna just for now. Let's imagine we're gonna think about the mv squared over r. So let's imagine we have a velocity v. We're driving around a circle of radius r, and we want to know why is v in there twice, right? Because it's a v squared. So this is something you should do whenever you get an equation. and has a square, you should ask yourself, why is that variable in there twice, right? It's r times r, or v times v. Why is that variable in there twice? Okay, so the reason it's in there twice is that velocity did two different things. Notice, if we have a bigger velocity, we have a bigger triangle. So if you have a bigger velocity, you have a bigger change in velocity. Imagine we increase the size of velocity to like here. Then our change in velocity would get bigger. So the bigger the velocity, the bigger the change in velocity. That was one source of V. The other source of V is that if we're going faster, it takes us less time to go through any given angle. So suppose in 1 second, if you're supposed you go for 1 second around a small circle and 1 second around a big circle. You go through a 1 circle around 1 second around a small circle, you go through a big angle. If you go through 1 second around a big circle, you go through a small angle. So you change both the angle and the size of the triangle. So the velocity comes in twice, hence v squared. So, and this is kind of a fun thing to do. Whenever you get an equation, you say, it has a square in it, you're like, oh wait, why is r in there twice? This way and that way. So that's just a fun little thing to think about. Okay. Let's keep thinking about force centripetal is mv squared over r. Suppose the radius were twice as big, and the net force to keep the car on the road would so imagine we have a car driving around a circle, driving around a corner, and if the radius were twice as big, the force needed to keep the car on the road would be okay. So this while you're thinking about this is like the problem I always think about when I think about centripetal acceleration. Okay, you're driving a car. There's a corner going around the radius, you need friction to keep you on the corner. Otherwise, you'll slide off. So frictional force holds you into the corner. If the road's banked, then the road road helps you in the corner. But let's imagine it's not banked. So it's a flat road. You're driving around a corner, and the friction on your wheels has to keep you going around the corner. This is why you slide off the road if it's icy and you go around the corner. And we're saying if the radius were twice as big, the net force to keep the car on the road would be what? Well, five, 4, 3, 2, 1. Okay, so equation, force centripetal is equal to mv squared over r. Okay, so if we're going to double r is in the denominator. So if you double something in the denominator, it's like putting a 2 in the denominator. It means your force is half as big as it used to be. So it decreases by a factor of 2. Okay, let's make sure this makes sense. So I have a picture of this later on in the lecture, don't I? So imagine this is our corner. So you might wonder, okay, what is a radius of a corner? if the corner doesn't have to go all the way around the circle to have a radius. What I mean by a radius of a corner is, imagine this is our little corner here. Here's our little car. It's going around a corner. And the radius is the radius of the circle that would fit the circle. Radius of the circle would fit the corner as it goes around. If you have a bigger radius, is that a sharper corner or a less sharp corner? It's a less sharp corner, right? So you're going around, it's this bigger, wider corner, so you don't have to turn as quickly. So if you have a bigger R, you need less force to keep you on the corner. This is why you typically slide off the corner on sharp corners. Right? If there's a sharp corner, that's a small R. You have a small R, that's a big force. You need a big centripetal force, aka friction, has to supply a big centripetal force to keep you in the circle. Okay, let's see the second one. Suppose the car's velocity is velocity. Now, we're doing velocity now. Suppose the car's velocity is twice as big. The net force to keep the car on the road would okay, 5, 4, 3, 2, 1. Okay, so some people think it's 4 times big, and some think it's twice as big. Okay, so if we take force centripetal mv squared over r, but now let's double v. So if we double v, that's like replacing v with 2v. 2v, which would come out to, you square that, so it would be 4mv squared over r. Okay, just kind of like up here, if we replaced r with 2r, we'd end up with a 1/2 mv squared over r. Here, if we double v, we end up with 4 mv squared over r. So the answer is number goes up by a factor of 4. Okay, so if you're going around a corner faster, you need a lot more force to keep you on the corner. Okay, this is why when somebody slides off a corner into the ditch, we assume one of two things. The corner was too sharp, but mostly they were going too fast. Because going too fast is what really matters. It's in there twice. If you have a going faster, or going twice as fast, you need 4 times the force to keep you on the circle. Okay. Suppose we're going around this corner, and we're going the direction shown. There's a little car here. It goes around the corner like that. When he enters the corner, so right here, as he's entering the corner, which direction is the centripetal acceleration? And you can see my little You want to zoom in? So hopefully that's enough to you can see. Here, I'll zoom in a little more. So here. Okay, 10, 5, 4, 3, 2, 1. Okay. So which direction we're going to accelerate? So we're going into the corner. Which direction are we going to accelerate? Acceleration is always towards the center of the circle. So we always accelerate that way. So we're, just as we're going, we always have to accelerate towards the center. Towards the center. Sound good? Questions? Okay. 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 Let's do a real world problem. Suppose the speed limit is V. The speed limit is V. For safety reasons, you don't want cars to have a centripetal acceleration of more than 0.5 gravity. What must the radius of curvature be? And let's just make this more fun. Let's give us a velocity. How fast are our velocity be? Let's do a freeway speeds. So 60 miles an hour is roughly 30 meters per second. So suppose we're going at 30 meters per second, and in order to avoid, if you go around, if you have too big of an acceleration, it's not good. You know, you'll knock the cars off. The drivers will feel queasy. And to give you a feel for, okay, what is 1G? Okay, if you accelerate forward at 1G, you're being pressed into the back of your seat just as hard as you're being pressed into the seat of your seat, because you have just as much backward force as you do have downward force. Okay. But when you go around a corner, you don't want the sideways force on the passengers to be anywhere near their weight, right? You wouldn't want the passenger to feel like they were sitting on the door handle, would you? So you want to stay well under a G. So let's assume you don't want to go over a fifth of a G. Seems like a very conservative and reasonable amount. So we don't want to go more than a fifth of a G, and we're going 30 meters per second, which is actually fairly modest speed for California freeways. How big does the radius need to be? Okay, so acceleration is equal to what's the centripetal acceleration? That's force. V squared over R. So if we want R is equal to V squared over A. So V squared would be 30 meters per second squared over A, which is 1/5 of a G, which is approximately 10 meters per second squared. Okay, so I get 30 squared times 5 divided by 10. So 30 squared is 9 with 2 zeros. So it'd be 5 times 900 over 10. And then my units, what happens to my units? I have meters squared over seconds squared over meters per second squared. I end up with meters. Okay. I cancel one of my zeros. I get 9 times 5, which is 45, 450 meters. You know how big 450 meters is? Half a kilometer. Almost half a kilometer. Which means the diameter of the circle would be a kilometer long. Okay, think about that. So here's our picture of our circle. So here's your car on the freeway going along. The diameter of that circle needs to be a whole entire kilometer, more than half a mile. Actually, roughly half a mile in this case. Freeways can't turn very fast. You ever look at freeways on a map? They don't turn very fast. And if they do, they have to put those signs up that say you have to drive slower. Because if you drive faster down the corner, you have to really slow down. Okay, so it's a big design consideration when you're designing freeways. Okay. Okay. Is this a maximum radius or a minimum radius? So suppose we do this calculation. We're building the freeway. We say we have to go. We're going 30 meters per second. We calculated this. It says a radius should be 450 meters. Is that a maximum radius or a minimum radius? It's a minimum radius. A radius was bigger than that, we'd be okay, right? Because we'd have less acceleration. This is our minimum radius, as quickly as you can turn. Okay. Questions about centripetal force? Okay. So let's do centrifugal versus centripetal. So if you read textbooks sometimes, or you go watch videos online, occasionally this thing called centrifugal force will show up. Centrifugal force is not a real force. It's a fictitious force. Doesn't really exist. Okay, but it kind of, some people feel like it does exist. Okay, suppose you're driving down the road and you turn right. And you feel a force on you, right, as you're in the car. Does the force push you right or left? Left, right. You're turning right. Think about it. You're turning right. You feel like a force is pushing you left. Imagine. So we can think about it with this picture up here. If you're turning right, the force feels like it's pushing left. Centripetal force, we've learned, always points toward the center of the circle. Centripetal acceleration is towards the center of the circle. So centripetal force is towards the center of the circle, which seems backward, right? Centripetal force says we should have our force. The force on you is actually to the right. Yeah, exactly. So your body wants to go straight. The car is turning. So it feels like you're being pushed to the left. You're not actually being pushed right. In fact, you're being pushed to the right. The car is pushing you to the right to get you to go to the right, whereas your body would just like to continue going straight. So if you imagine that you don't look at, you're a passenger, the windows are all covered, and you're blindfolded. You don't know that you're turning. All you know is you're being pushed. Except for you feel like you almost feel like you're being thrown to the left of the car, right? And the reason you feel like you're being thrown to the left of the car is that the car is accelerating. It's this weird accelerating reference frame. In physics, we don't like to think about accelerating reference frames. It's goofy stuff happens, like forces go the wrong directions, and you get strange F equals ma stuff. So usually we don't do force. Usually when we do physics, and I recommend you do this, always say the real force is the force towards the center. It's the force needed to turn you. Some people like to say, oh, let's imagine you're not turning. Pretend you're in a car, you're not turning, but there's an extra fictitious force pushing out. And they call that fictitious force mv squared over r. They call it the centrifugal force instead of centripetal. That's useful for solving problems sometimes. Sometimes it's easier to think about. You can draw it in a free body diagram, pretend there's no acceleration, and instead there's a force going the other direction. It'll work. You can solve problems that way. I don't recommend it. I recommend you think about it's actually accelerating. The force is always towards the center. If that discussion didn't make any sense, that's fine. You don't need to know anything about centrifugal force. It's not real anyway. So you can do everything just with regular old centripetal that we've talked about, but now you just are aware of its existence of this thing. Okay. Questions? Okay, so we have 15 minutes left. I'm gonna do an activity. We're gonna do an estimation activity. This is a fun one. It's a little dated now, but back in, it was more like an 80s thing. People got these things called waterbeds. Maybe some of you still have them, where you literally, it's a bed where the mattress is a big flexible bladder thingy of water. That's literally what it is. It's like you know how you have a blow-up mattress? It's like a blow-up mattress, but instead of blowing it up with air, you blow it up with water. Literally take a hose, blow it, and fill it up with water. Okay, so imagine you have one of these, and you want to know how much it will weigh.
What size, what shape?
Yeah, okay, so this is an estimation question, right? We have to decide, is it a king size, is it a queen size?
Or
I
is
don't
it a circle?
Oh, okay, well, wait, that's
even more 80.
that is even more easy. Okay, let's just go with a regular old, I don't know, queen size or something.
Okay.
So we have a queen size mattress, and how big is a mattress? I don't know. I mean, how big is a mattress? Y'all see a mattress? Most of you want them. You know, you have an idea how big a mattress is. Estimate if your mattress was full of water. How much would it weigh? Okay, you feel free to work with each other. We'll take some time to estimate that. I don't need to get an exact value, just get a rough value.
About, no. I was thinking, no, that's I built my own bed, so I should know. And you want to make it a tall one? Yeah. Do you want to do like 15 inches? Yeah.
Yes, definitely. That's low.
And you should convert it to pounds, unless, I mean, some people are like good at thinking of large things in kilograms. I personally, being an American, know things in pounds, but better than kilograms. So convert it to pounds. Good conversion. 2 pounds, 2 pounds mass is roughly a kilogram. Yes. Okay. Hold on to that. That's a good, you should get the answer and you should go, does that make sense? Have you ever picked one up? No. Okay.
I'm assuming that'd be extremely hard. You go over 4,000 pounds.
Okay.
Kilograms.
Okay, guys. Few more minutes.
Divided by 1,000 kilograms.
Okay.
Which makes sense.
Okay, let's do a calculation again. Okay, so let's first come up with what approximately should our dimensions be. So we're gonna have a length, a width, and a height. What should our length be? 7 feet. 7 feet. Okay, what's our width? What?
About 5 feet.
5 feet. And our height? 1 foot. Okay. I don't like feet. They're not really good for English metric units. Okay, so 7 feet is about how many meters? Meters. The meter. And 2 meters. Right, about that far. It's a little over 2 meters, but not that much over 2 meters. What's 5 feet? Well, it's going to be a little under 2 meters. So maybe I'll do a little less than 2 meters. But let's just do 2 meters. Maybe this is a weird, I mean, because this is a little under, this is a little over. So if we have an underestimate here and an overestimate there, they'll cancel each other out. It'll be about the same. And how about 1 feet is about, 1 foot is in meters is about, it's actually pretty close to a third. If you think about a yard and a meter are almost identical, like a little bit off. So if a foot is a third of a yard, so a foot is roughly a third of a meter. So I'm going to say about 1/3 meters. Okay, so I have 2 meters times 2 meters times 1/3 meter gives me 4/3, which is what, 1.3 meters cubed. Okay, so if we have 1.3 meters cubed, that's the volume. How do we get the mass? Density. Density is, okay, so if we went mass equals density times volume. So we have density, what's the density of water? So some people do kilogram per liter, some people do gram per cubic centimeter, or milliliter, whichever you want. I like to do kilogram per liter. So 1 kilogram per liter, our volume is 1.3 meters cubed. Okay. Oh, here, I should stop share so people on Zoom can see this in higher definition. Is this pointed right, Leah? Okay. I have to get liters to cancel with cubic meters. How many liters are in a cubic meter? Okay, well, another way to do this is suppose we did 1 gram per centimeter cubed times 1.3 meters cubed. There's 100 centimeters in a meter, and then we have to cube that. But then there's a 1,000 grams in 1 kilogram. So we get 2 times 3 times 3. So 6 zeros in the top, 3 zeros in the bottom. That gives us a net of 3 zeros. So you can just use your calculator too. I'm just doing mental math. That'll give us 1.3, but times 1,000. So 1,300, 1,300 kilograms. Which is roughly, kilograms about 2 pounds. So that's roughly 2,600 pounds. For context, a ton is 2,000 pounds. Okay. Waterbeds are really heavy. You ever seen an apartment that say no waterbeds? Okay, occasionally you'll assign up for apartments and one of the requirements will be no waterbeds. The reason, some floors aren't strong enough to support them. You wouldn't want to fill up your waterbed and have it come crashing through the floor. They're heavy. Yes?
How did you go from kilograms?
Those are the same.
Oh.
There are 1,000 cubic centimeters and cubic centimeter is a milliliter. It's the same thing. A milliliter is a cubic centimeter. There's 1,000 of those in a liter, right? So the mill is 1,000. There's 1,000 grams in a kilogram. If you have 1,000 grams and 1,000 milliliters. Okay. And then my wife insisted I do a demo for today's class on some typical force. So we're doing a demo with you. And that is, we're going to take some water. Here. Okay, I'm gonna get wet, right? So I'm gonna go like this. Okay, and I go. And I didn't get wet, right? Why? So, stop. Okay, so imagine the buckets at the top. What are the forces on the water? Gravity? That's about it. Well, actually, it's probably, I'm also probably pulling down on it, actually. Okay, why doesn't the water fall out? It is falling. It is going down. It's accelerating downward. It's just the bucket is accelerating down faster. So the bucket's keeping up with it because the bucket is accelerating down at centripetal acceleration, right? Because when the bucket's at the top, it has to accelerate down just to keep going around the circle. And the centripetal acceleration of my arm is bigger than the centripetal acceleration of gravity. So it keeps it going down. The bucket is basically accelerating down faster than the water. So the water stays in the bucket. Okay. See y'all on, well, see some of you tomorrow and the rest of you on Wednesday. Yes, otherwise it would have fallen out. Yeah.